Okay, so we had our first project, Project A. My phone just went. Okay, so we had our first heat transfer project on conduction, and we did Project A, which was transient conduction through a plane wall. We started off by doing our givens, assumptions, and schematic. Our schematic down here is 25 centimeter thick plain wall with 10 centimeters of brick and 15 centimeters of insulation. We divided our wall into 27 nodes with a delta X of 0.01 meters. This created 4 half nodes, 1 on each end and 2 in the middle, which we'll talk about later. The outside is subjected to convection with a varying temperature of 30 degrees Fahrenheit to 70 degrees Fahrenheit over the course of 12 hours, which is also equal to about -1 degrees Celsius to 21 degrees Celsius over the same 12 hours. There's an initial temperature of 20 degrees Celsius across all of the nodes. It is a transient problem, and we looked up our K constants, our density, and our specific heat constants for both the brick and insulation. So then we developed our nodes. So node 1, which would be on the outside closest to the varying temperature, is experiencing convection from that outside temperature and conduction from the brick. So that is what this equation represents. There is an equation for T2 through T10. So the middle section of the brick layer that is not touching the convection nor touching the insulation. And then a very similar equation for node 13 through 26, which is the exact same thing, but on the insulation part of the wall. T11 and 12 are specific equations. Because both of these nodes are experiencing conduction from brick and from insulation, they have similar equations. However, T11 is experiencing conduction via the brick over an entire node or entire delta X, and experiencing conduction through the insulation only over half of a node. And the opposite is true for T12. It experiences conduction over half a node through the brick and over an entire node for the insulation. So they have very similar equations, but slightly different in the constants. And then the very last node is modeled with experiencing convection on one side on the innermost part of the wall and conduction via the insulation part of the wall. So then we're going to show you our Excel file.
All right. We chose to go with Excel since that's what we're most comfortable with working in. Here on our left-hand side, we have all of our constants and all of our looked up values. These all relate to our M and our FO. As you can see, they're all linked in here. And we can change, let's say, the K of the brick. If we change this to 2, we can see our FO of brick change, our M of brick change, and we can also see our entire spreadsheet change. Let's go back and replace that. For our M values, we have particularly high ones, but this was necessary because when we had a higher delta T, we found our spreadsheet would break after a couple hundred data points. And that's not what we wanted. So we had to lower it down to 5 seconds per delta T. And that made our spreadsheet real nice, but it also gave us around 9,000 lines of code. Here we have our temperature outside as a sine function. We can go in here and see the equation. It's a sine. And then here we have node 1. We can show you that special equation where it draws from the H from the outside and the temperature from the outside, as well as its previous temperature and its neighboring node temperature in the previous time step. And then here we can show you the equation for 11 and 12, which is slightly different from the other internal node temperatures. Here you can see we have a 4 where it takes from the half node, which is node 12 in this case. And now we can go all the way to the bottom and show you our temperature gradient at the last time step. Okay, so here we have our final temperature gradient in the last time step. Looks very good, highest on the outside, lowest on the inside. And here's a graph of temperature versus time. The gray top line is the inner insulation temperature. Doesn't change much, stays around 19.8 to 20 the entire time. But the outer brick temperature does also start at 20, but it changes more drastically due to that higher K value and more closely follows the outside air temperature. Now we have our plot for highest temperature at each node. And this plot was a little confusing, but then we realized that every node starts at 20 degrees Celsius. So the majority of the nodes, except for the ones closest to the outside, would all have a maximum temperature of 20. And this is our lowest temperature at each node. And this is exactly what we were expecting to see. We can see that the K nodes all have a steeper slope due to that higher K value, and the insulation nodes all have a lower slope due to that lower K value.
So we're pretty confident in the accuracy of our results. One problem that we had was making sure that T11 and T12 nodes were differentiated. Initially, we represented it as two half nodes, where the very middle of those two half nodes would represent one single temperature for both of those areas. However, we can't really model a node that has two different materials like brick and insulation. So we instead decided to add another node, call it node 12, have 11 and 12 equal virtually the same thing, but by making them two different equations, they will have to inform each other, which makes a lot more sense according to how heat transfer naturally happens through this wall.
Thank you for watching. Cool
All right.
sauce.